In a world where this week on the third episode of the first season of Chemistry Unsolved, we investigate the chemical bonding, the mysteries of the ionic bonds, as part of our ongoing investigation into the question, how can chemistry solve this?
My name is Ariane.
Mark here.
I'm Grace.
This is Catherine.
My name is Lawrence, and this is Chemistry Unsolved.
Hi!
Hi,
Hello.
Hi.
Hello.
welcome to another episode of Chemistry Unsolved.
Yes. Ionic bonds, octet rule, Lewis structure.
I think we're gonna have an interesting case to investigate in this episode.
Have you guys already encountered something about this case?
Well, not really.
I'm not quite sure.
How about you, Catherine? You love chemistry, right?
I'm a bit familiar with it. I've read some files, you know.
Yeah, some of the concepts here have been introduced in the past episode.
Alright, then let's get into it.
Look,
In the first part of this week's episode, we'll be investigating the ionic bonds and ionic bonding. According to sciencenotes.org, ionic bonds are, quote, the type of chemical bonds that holds together metal atoms with non-metal atoms, end quote. Whenever we have a chemical that has a metal connected to a non-metal, the compound is held together by ionic bonding. It is also called electrovalent bonding, a type of linkage formed from the electrostatic attraction between oppositely charged ions in a chemical compound. The transfer of one or more electrons between atoms produces negative ions called anions and positive ions called cations, and these ions attract each other. Ionic bonds can be formed after two or more atoms lose or gain electrons to form an ion. Some examples of these are sodium chloride, magnesium oxide, and aluminum oxide. Each one of these chemicals have metal and non-metal atoms.
Ooh, that's quite a mouthful, huh? We're not talking about electrons, electrovalent bonding, and electrostatic attraction.
I guess we really need to get our braces working in this case, huh?
yeah, I hope that wasn't too heavy for you guys. We still have a lot to get into, so let's continue with the investigation. The octet rule. Now let's talk about the octet rule. The octet rule refers to, quote, the tendency of atoms to prefer to have 8 electrons in the valence shell. When atoms have fewer than 8 electrons, they tend to react and form more stable compounds. End quote. Just a quick recap, the outermost shell of an atom is called the valence shell, and the electrons that reside in the valence shell are called valence electrons. Let's use fluorine as an example. As we can see in the picture, the outermost shell of fluorine has only 7 electrons. These electrons are the valence electrons, and the outermost shell where it resides is the valence shell.
So, from what you discussed, right now, chlorine does not satisfy the octet rule, right? Because its outermost shell only contains 7 electrons instead of 8.
Yes, that's right. As I have mentioned a while ago, when atoms have fewer than 8 electrons, they tend to react and form more stable compounds.
Based on this presented piece of evidence, the noble gases are the chemical elements in the group 18 of the periodic table, right? This group includes helium, neon, argon, krypton, xenon, radon, and the synthetic element oganesson. Noble gases are highly stable because of their electronic configuration. They have a full outer shell of electrons, making them already in their most stable state. Just like stated in the octet rule earlier, an element needs 8 valence electrons in their outer shell to become stable, so other elements bond with each other to create a stable compound.
And due to the electronic configuration of noble gases and their valence electrons, they rarely react with other elements since they are already stable, and thus there is no need for the atom to lose or gain electrons.
Now, for us to further understand the octet rule, let's take a look at this example of an ionic bonding. The reaction between an atom of sodium and an atom of chlorine. Sodium is an alkali metal and chlorine is a halogen. It is important to know that metals like to give electrons, so they form positively charged cations, and nonmetals like to receive electrons, so they form negatively charged anions. By losing those electrons, these metals can achieve noble gas configuration and satisfy the octet rule. As we can see, sodium only has 1 electron in its valence shell and chlorine has 7 valence electrons. The sodium molecule donates the lone electron in its valence orbital in order to achieve octet configuration. This creates a positively charged cation due to the loss of electron, and the chlorine atom receives 1 electron to achieve its octet configuration, which creates a negatively charged anion. The charges on the anion and cation corresponds to the number of electrons donated or received. In ionic bonds, the net charge of the compound must be 0. The octet rule could have been satisfied if chlorine gave up all 7 of its valence electrons and sodium took them. In that case, both would have the electron configuration of noble gases, with a full valence shell. However, their charges would be much higher. It would be Na 7- and Cl 7+, which is much less stable than Na+ ion and Cl+ Cl- ion. It is more energy efficient for chlorine to gain 1 electron than to lose 7. Atoms are more stable when they have no charge or only a small charge. To summarize, according to the octet rule, the sodium atom, which only has a single electron in its outermost shell, uses the electron to get a stable configuration like gas, while the chlorine gas with 7 valence electron gains an electron from the sodium atom to obtain a stable configuration like the argon gas.
Now, let's get into the next part of this week's investigation, the Lewis structure of ions. According to thoughtco.com, the Lewis structure is, quote, a representation of a molecule where dots are used to show electron positions around the atoms, and lines or dot pairs represent bonds between atoms, end quote. Named after Gilbert N. Lewis, an American chemist who introduced the idea in the article The Atom and the Molecule in April of the year 1916. Do you think he's a nice guy? Look at him.
I mean, yeah, but do you know what his middle name is?
No, I have no idea whatsoever. What?
It's actually Newton.
Oh, Newton. There's something about Newtons and science, you know?
No, 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 no. I think they're not related at all.
They may be. Look at their pictures. Not that they're lookalikes, but there are no happy pictures of them. They're all grumpy and serious in these.
That doesn't make sense, but okay.
Look at our next example, magnesium fluoride. Magnesium is a metal with two valence electrons. Fluorine is a nonmetal with seven valence electrons. Fluorine is a halogen, so each fluorine atom only wants just one electron. Magnesium has two electrons. One of those will go to the first fluorine atom and the other one is going to the second. Remember that a full arrow represents the flow of two electrons and a half arrow represents the flow of one electron. Let's now write them inside brackets. When magnesium gives away its two electrons, it's going to obtain a 2 plus charge. When fluorine obtains one electron, it's gonna have a minus one charge. We'll just put a minus sign, then we need to write the four lone pairs around each fluorine ion. And so, this is the Lewis structure for the ionic compound magnesium fluoride.
Now let's look at the last example, potassium oxide. So we have two potassium ions in this formula, and we're gonna draw two potassium atoms and one oxygen atom. Each potassium atom contains one valence electron. Oxygen is a chalcogen that has 6 valence electrons, and oxygen needs 8 valence electrons, so it's gonna need to acquire 2 electrons. Therefore, in this example, each potassium atom is going to give one electron to the oxygen atom so that it can have two to complete the 8 valence electrons. Now, let's put oxygen in the center because it has a bigger charge. Because oxygen obtained 2 electrons, it's going to have a 2- charge. On the other hand, each potassium atom gives away 1 electron, so they will both have a +1 charge. We're just going to put plus signs. So this is how we can draw the Lewis structure for potassium oxide.
These are the other pieces of evidence that helped us in solving this case. That's all for now. See you next week for another investigation of another case here in Chemistry Unsolved. Bye!
Bye!
Bye.
Bye! See you!
Bye.
Bye-bye.
The case of chemical bonding, the mysteries of the ionic bonds, has now been closed. We may never be able to fully understand some concepts in chemistry right away. Deeper investigation and comprehension may sometimes be needed. However, we hope that you have learned something from this episode. Whether or not you've watched and listened to this week's investigation till the end, will continue to remain unsolved.